This is the fifth and final section of the complex numbers chapter, chapter 1 in the core 1 book, and this is solving cubic and quartic equations. So we've already done quadratics. A cubic, well, that's going to go up to x cubed. There's an example of what a cubic looks like here. So we start with z cubed. So these things are going to have maybe complex roots, and a quartic goes to z to the power 4. So there's an example there of what it looks like. So this is a cubic, this is a quartic, and what we want to be able to do is to find all of the roots of these. Now, when we had a quadratic, the options were one real root, two real roots, or two conjugate, or one conjugate pair. Two pairs implies that there's 4, but yeah, one conjugate pair. It's actually 2 roots there. Okay, when we come to a cubic, right, the options are one real and, so one of the roots is real and the other 2 are a conjugate pair, or you could have 3 real roots. Yeah, these complex roots always come in pairs, so you could have either one real root with a conjugate pair or 3 real roots. So I'm guessing, because this chapter is all about complex numbers, when we have quadratics, it's going to be things that are like this. When we have cubics, it's going to be things like this. The other stuff is reserved for normal maths lessons. And then the last type is a quartic. We've got more options. So with a quartic, you could have 4 real roots. Okay, so that's going to be for normal maths lessons. We could have 2 real and a conjugate pair. Yeah, so that makes the 4 roots. So we'll be interested in those. Or we could have 2 different conjugate pairs. Yeah, so these are the ones we're going to be interested in. Now, just like we did with the quadratics, once we know one root, if they come in a conjugate pair, then we can work out the other one. Yeah, so if one root is a plus bi or ib, then its conjugate is going to be a minus bi, so we would just reverse the sign in front of the imaginary part. Now, before completing this section, you need to have made sure that you have done the factor theorem from your normal maths lessons, or if you haven't done it, that at least you've taught yourself how to do it, and also algebraic long division. Yeah, so if you haven't done those in your normal maths lessons, then you'll need to find a way of learning those before you complete this section. Okay, given that -1 is a root of that cubic, find the value of k. Right, so we're going to be using the factor theorem. The factor theorem says that if x equals a certain number, here is a root, then f of -1 should equal 0. In other words, if I substitute in -1, I'm expecting 0. So basically, I'm going to substitute -1 for z, because that's going to be a root. So just say let z equal -1. So I'll get -1 cubed minus -1 squared plus 3 times -1 plus k equals 0. So I should be able to find the value of k. So from there, -1 cubed is -1. Then we have negative 1 squared, which is 1, so you minus 1 again. Then minus 3 plus k equals 0. So that means that k equals, what have I got? Negative 5, so it'll be k equals 5. So we found the value of k by using the factor theorem. So I could actually write the full cubic as z cubed minus z squared plus 3z plus 5. And this is probably what I'm going to be using in part B. Now part B says find the two other roots. Now the two other roots are going to be complex roots. So I only need to find one. And then once I've found one, I just find a conjugate of that for the other root. Now to find what that root is, I need to use algebraic long division to reduce the cubic down to a quadratic and then find the roots of that quadratic. So I'm going to have z cubed minus z squared plus 3z plus 5. I'm going to be dividing it by a factor, so this goes with the factor theorem. If if z equals negative 1 is a root, therefore z minus negative 1, like that, is a factor. That's the factor theorem. So in other words, z plus 1 is a factor. So I'm going to divide this by z plus 1 using algebraic long division. Right, okay, so the first thing is going to be how many times does z go into z cubed? It goes into it z squared times. Now I do z squared times z, and z squared times by 1. Sorry, that's z squared times by z should be z cubed, and z squared times by 1 is z squared. So we now subtract. Z cubed minus z cubed is nothing. Negative z cubed. Subtract positive z squared. So I think I said z cubed. Z squared is negative 2z squared. Bring down the 3z. Now we say how many times does z here go into negative 2z squared, and that's going to be negative 2z. Then we multiply a factor by negative 2z, and that's going to give us negative 2z squared, and then times it by 1, negative 2z. Now we're going to subtract. So I keep putting the wrong power down, that's squared. I said squared and I wrote cubed. Right, okay, so that means the z squareds will cancel. I end up with 3z minus negative 2z, which is plus, which gives me 5z. Bring down the 5, this is looking nice. How many times does z go into 5z? 5 times. And then 5 times z, 5 times 1. Okay, no remainder. Well, that's another way of proving that negative 1's a factor by long division, but the factor theorem is quicker. So that leaves us with this quadratic, which we're going to use to find the other roots, and we can do that by completing this square, or we can use the quadratic equation. So I'm going to use the quadratic equation to work out what the other roots are. So with the quadratic equation, I have a equals 1, b equals negative 2, and c equals 5. So minus b minus negative 2 plus or minus the square of b squared negative 2 squared minus 4 times a times c all over 2a. So from there I will get 2 plus or minus. Now I end up with 4 minus 20, which is negative 16. So plus or minus the square root of negative 16. So here I can see the complex roots come in. Now I did 2a. I really should have put 2 times 1 here. So 2 times 1. So 2. Now we should be able to actually work out what those roots are, or that negative root negative 16 without actually having to split it up. So it's going to be 4i, yeah, all over 2. So split that up, we get 2 over 2. Sorry, not 2 over 2. Divide the whole thing by 2. So we end up with 1 plus or minus 2i. So now we can finish this off by writing all of the roots. Find the other two roots. The other two roots are 1 plus 2i and 1 minus 2i. So we get both roots. So it's not as if we got one and we had to find the other. I think I said that a bit earlier. But actually, the reason we get the conjugates is because of this plus minus. Yeah, this bit is going to be imaginary. So you're adding the imaginary, minusing the imaginary. So the plus minus here in the quadratic is the bit that ends up giving us the two conjugates. Okay, given that 3 plus I is a root, solve that quartic and solve completely. So if one of the roots is 3 plus y, so if one root is 3 plus I, the other is 3 minus I, okay, because they come in these conjugate pairs. If I have those roots, I can find a quadratic that gave those roots by basically working out what this is, okay, by expanding the brackets. But I have an easier way. Remember, if our roots are alpha and beta, and our case, one is 3 plus I and one is 3 minus I, and the real part of our roots we call a, which is 3, and the imaginary part of our roots, which is the number in front of I, which is 1, then we know that the quadratic that we get is going to be z squared minus alpha plus beta z plus alpha times beta. But we also know, we worked out that alpha plus beta is just 2a, and alpha times beta is a squared, the sum of 2 squared, a squared plus b squared. So we're going to use that to find a quadratic. That's the quick way of doing it. So what we're going to get is z squared minus 2 times a. So that's going to be minus 2 times 3z. And then we're going to have plus a squared plus b squared. So I suppose what you could do is you could take this and you could say, right, z squared minus 2az plus a squared plus b squared. So that is another way of finding our roots. That's where the roots are a plus bi and a minus bi. Yeah, that's a very quick way of doing it. So what that gives us is z squared minus 6z plus 10. Now we're going to do algebraic long division on the quartic. So this z squared minus 6z plus 10 is called a divisor. Okay, and when we divide this quartic by the divisor, we'll end up with something at the top, and that's going to be a quadratic, and that will use to find the other two roots. So here we go. Right, So z squared goes into 2z to the power 4 2z squared times, so 2z squared. Multiply that by the divisor, so that becomes 2z4 minus 12z cubed plus 20z squared. Now subtract. So I'll have negative 3 minus 12 or plus 12, so 9z cubed, and negative 39, and then that's going to be minus 20, so it's going to be negative 59z squared, plus bring the next term down, do the whole process again. So z squared goes into 9z cubed plus 9z times, multiply by the divisor, so 9z cubed. 9 times 6 is 54, so negative 54 z squared, and then plus 90z, subtract, let's see what's left. So negative 59 minus negative 54 will give me negative 5, so minus 5z squared, and then 120 minus 90 plus 30z minus 50. Okay, how many times does z squared go into minus z squared? Well, minus 5 times. Multiply everything by minus 5, 5z squared plus 30z minus 50, which is what we wanted to happen. We don't want a remainder. Yeah. So now what we're going to do, we're going to find the roots of this. Now the roots could be real or complex. They come in a pair. Right. So let's use the quadratic equation with a equal to 2, b equal to 9, c equals negative 5. So we now have minus b, minus 9, plus or minus the square root of b squared minus 4 times a times by c all over 2a. So it's going to give us the other roots. So you've got negative 9 plus or minus. Now we end up 9 squared is 81. So you've got 81 minus 4 times 2 times negative 5. So this looks like it's going to be positive. Yeah, 121. So not a negative under there. So the next two roots are going to be real. Over 4. So from that we get well, that's 11, isn't it? So 9 plus or minus 11 over 2. So that will give us, well, 9 plus 11 is 20, over 2 is 10. And then 9 minus 11, which is negative 2 divided by 2, will give us negative 1. Okay, so all of the roots we have are 10, negative 1, 3 plus I, and 3 minus I. Right, I've just spotted an error. I've put, and hopefully you spotted it as well, you can see that I've put 4 here, and for some reason I've changed it to 2. So hopefully you're still watching and you've realized that mistake. So those bits here are going to change. So let's get those right. I don't know why I did that. I wrote 4 and changed it to 2. So yeah, this should be 4. So now I get 9 plus 11, which is 20 divided by 4, which is oh, and this is negative as well. Right. Yeah, so negative 11, oh, so negative 9 plus 11 is going to be 2. 2 over 4 is a half. And then if I do negative 9 minus 11, that's negative 20. Negative 20 divided by 4 is negative 5. So the correct root should be half negative 5, 5 plus 3i, or 3 plus I and 3 minus I. Okay, I'm going to show that z squared plus 4 is a factor of that quartic, and then carry on and completely solve it. So the way I'm going to show that it's a factor is I'm going to use long division, and if it's a factor, after I do long division, there should be no remainder. Now, to make sure I don't run into any problems, this divisor of z squared plus 4, I'm going to write as z squared plus 0z plus 4. That way I get things in the right columns. I don't miss anything out. Otherwise, we could run into problems. So anytime you've got a missing power in the divisor or the actual thing that you're dividing, put it in as 0. So z to the power 4 minus 2z cubed plus 21z squared minus 8z plus 68. Z squared is in z to the power 4, z squared. Multiply everything by z squared. So you get z to the power 4. We get 0z cubed. And then we get 4z squared. Subtract. So we'll end up with negative 2z cubed plus 17z squared, 21 minus 4, 17. Then bring down the 8. Then how many times does z squared go into negative 2z cubed minus 2z times? And we multiply negative 2z cubed plus 0z squared, and then minus 8z. Subtract. So we end up with 17z squared, and that becomes 0z. So I write it down as 0z plus 68. How many times does z squared go into 17z squared? 17 times. So times by 17. And then 4 times 17 is 68. That's nice. Which gives us no remainder. So we can say something like, therefore, z squared plus 4 is a factor. Yeah, because we have no remainder. Right, now can we get 2 of the roots from that? Z squared plus 4. Well, if it's a factor, that means z squared plus 4 will give you 0, which means that z squared equals minus 4, which gives us the roots. If you square root both sides, square root of negative 4, so 2i and negative 2i. To get the other 2 roots, we look at this and we want to factorize that. I'm going to use the quadratic equation. Factorize, we'll find out what the roots are. C17. So minus negative 2 plus or minus square root b squared negative 2 squared minus 4 times a times 17. That 4ac is bigger than b squared. So, and it's negative, so it looks like I'm going to have two more complex conjugate roots. So we get 2, so basically we're finding z here, aren't we? So we're going to get 2 plus or minus. Now we're going to get 4 minus 68. Now 4 minus 68 is negative 64 over 2. So that gives 2 plus or minus, so we should be able to do this without too much work, 8i. And then from there we'll get 1 plus 4i, 1 minus 4i. So our final answer for all the roots together in one place, 2i minus 2i, 1 plus 4i, and 1 minus 4i. Right, you should now be able to do exercise 1F on pages 13 to 14, and then when you've done that exercise you should now be able to go on to the mixed exercise on pages 14 to 16.